supposed to start at 9, so let's not dilly-dally. I'm going to start recording. Okay. So, screen 1, I think? Yes. Okay. Good. Can someone confirm in the chat whether or not you can see my screen, and also whether the audio is working okay? All right. Thanks. All right, then. So, hello, everybody. This is Complex Differential Geometry. I have been instructed from on high that I can't call it a course. So, it's a lecture series. And so, we're going to be um, going through like the introductory topics in complex differential geometry. I would like to kind of cover the basics, kind of give people a lay of the land, but please bear in mind that I'm also kind of learning complex differential geometry while I'm doing this. This is my kind of first formal lecture series, so I'm bound to like make mistakes, especially with very subtle points every so often. So if you see that I do something like that, you can field it during the questions, or we can talk about it after the um, lecture is over um, on the Discord. I think the lecture series will only be improved by people discussing the all of the points. Right. And another thing is that the thing about the whole course versus lecture series thing, I'm legally obligated to disclose that you won't get any credits for anything by coming to this lecture series. It's just all you get is me rambling about complex differential geometry, and hopefully the takeaway is that it gives you a solid foundation for studying complex differential geometry more formally, gives you a solid basis to start off from. And hopefully it's kind of like a collaborative process where there are obviously people in the audience who know complex differential geometry much better than I do. So hopefully by discussing everything together, we come to a good understanding of the topics. So what topics are we going to talk about? Today we're going to talk about real differential geometry. This is going to be a a brief review of it. So we're doing real diff geo. And today is the only day that we're going to be doing anything in the real space. So from tomorrow onwards, well, tomorrow, I mean next lecture. From next lecture onwards, we're going to be focusing purely on the complex version of the manifolds. But given that this is like the immediately previous prerequisite for this and something that I had to devote the first lecture to this. Right, so let's get into it. The first thing that I want to talk about with differential geometry is talking about the idea of so a topology is well, you start with a set X, and you take subsets of so the elements of this set X are called points. So we have points on this as the elements, and we take subsets of this set X and we put them in a set of subsets. That this thing is called the topology. And the elements of the topology are called open sets on X. So this is a choice of topology. You can have multiple topologies on the same set, and what you get, this pair is called a topological space. Right. So using the open sets in tau, we can define this notion of, let's say I have this point P that we take from X. We have this notion of, well, let's say we have take an open set. This is like U element of tau, and this defines a neighborhood, a local neighborhood. I'm going to shorten that, neighborhood of P. And we could say that P and Q are close together if there's an open set that contains both P and Q. And notice that we're only using set theoretic notion so far. So we don't need to like think of these points as being close together or farther away from each other or something like that. Um, and these local neighborhoods are very interesting. They allow us to define certain properties uh, of this space, this topological space. It allows us to think about things like the connectedness of the space, the compactness of the space, um, things like continuity on the space. We base all of these concepts on uh, we define them using this idea of things being in local neighborhoods using open sets. And so without getting too much into the details of this, because that's not the point of the course, I just wanted to point out that these are all qualitative properties. Qualitative properties. So when we go from a set to a topological space, we have this space where all of the properties that the topology can see are all these qualitative properties about the space. But when we're doing geometry, we have this idea that geometry is about distances, angles, things like curvature. These are not defined on a topology because, well, to illustrate this by example, a very nice topological space is a sphere. Is a sphere, S2, and we can continuously deform S2 into some arbitrary shape, and this would still be the same in terms of a topological space. And so there's this notion of the fact that in a topology you can't really like, there's no definite shape, there's no definite size for what the space looks like. So it's hard to define something like distances, angles, and curvature when the shape is when this space is like allowed to continuously fluctuate. So what we say is that these two spaces are homeomorphic to each other. And what homeomorphic means is that to a topologist, their structure is the same. Essentially, corporate wants you to tell the difference between these two pictures, but you're a topologist. So, and so we what we would like to do in order to do geometry on this space, we need to add additional structures onto this topological space so that we have some notion of distances, angles, and curvature, which in order to do that, we need something called a metric. Now, we're going to get to metrics later because first of all, we need to define some more things, and that's where the differential part of differential geometry comes in. So we are talking about differential geometry, and so it's easier to define the differential part first, which really just means that we want to define how to do calculus on this space. And when we add this structure, so there's some structure that we're going to add that is going to turn our topological space into something that we're going to call a manifold. And specifically, once we want to do differential geometry, we're going to want a smooth manifold. And when we want to do complex differential geometry, we will want a complex smooth, or I suppose you would call it a smooth complex manifold. But yes, so that's what we want to work up to. So today we're just going to work on this part. We're going to build up what a smooth manifold is. And then later we're going to look at some interesting spaces that you can define on a smooth manifold. Okay, so first things first, so general topological spaces can be pretty bizarre. So there are things like the line with two origins. So so there's a space called the line with two origins. And on this in this line, there are 2 points at the origin, and they cannot be separated from each other. And kind of intuitively, we understand that this is not the kind of thing that we want for a space that is conducive to doing geometry on, at least the kind of geometry that we want to do. So so we impose, number one, a niceness property, which is called Hausdorff, the Hausdorff property. What the Hausdorff property says is that, let's say that I have a point P and a point Q. The Hausdorff property says that we will always be able to find an open set UP and an open set UQ such that UP intersection UQ is empty, so that they're disjoint, they don't overlap. This is what it means for us to be able to separate 2 points in our topological space. So the first thing we want is for the space to be Hausdorff. And then there are other issues, like there is this topological space called the long line. Very interesting. So you take a copy of 0, 1, which is closed on one end and open on the other end, and you string together an uncountable number of these together. I mean, this is not a rigorous illustration. This is just for kind of intuition purposes. But this line doesn't have a countable basis set. So we didn't talk about bases with topology, but a basis is basically like a set of subsets of the topology that by taking the union of them, you can come back to the entire topology. So it's very much like the basis of a vector space, where you can reconstruct all of the vectors in the vector space from the basis vectors. So you can reconstruct all the open sets in topology from the basis of the topology. And we would really like for our basis to be countable. And that brings us to the second property, is called second countability. Second countability ensures that this basis is countable, and it's equivalent, along with the Hausdorff property, it's equivalent with this thing called paracompactness, which has the niceness property that if we can always embed. I never like keep straight whether it's embed or embed, but we can embed it in sufficiently high dimensional Rn. So yeah, and the third thing that we want, which is this is less of a niceness property and more of the definitional, um, what is going to define something to be a manifold, is that um, we want, in order to be able to eventually do geometry on this space, we want it to be the case that if we zoom in to a small patch of the space, eventually it starts looking like Rn. Now that's an intuitive idea. Okay, if I zoom in, then it should kind of look flat. That's like the flat Euclidean space. But so we can formalize that. We can say that, well, our space, if we have U element of uh, tau in the space in T, then let me see if I'm getting this right. No, right. For P in M, so for any point P in M, there will exist an open set UP such that uh, UP is homeomorphic to Rn. So with all three of these properties, so this is a specific sense in which we are saying that if you zoom in, our space will look like Rn. And whenever we want to bring up this property, we will use this definition to um, to as our jumping off point. So when we have all three of these properties, we get a specific kind of space called a topological manifold. So now that we have a topological manifold, the topological manifold is not yet rigid in that sense that we need for doing geometry on. It has some good properties that we will use in order to get the differentiable part up and running, but we'll have to do the geometry part a little later. Right now, the topological manifold is still that kind of rubbery space that you can stretch and squeeze, but it has some. We basically discluded some what mathematicians would call pathological spaces. Um, so, right. Uh, so the next thing that we want to do is, so now that we've kind of filtered down to some nicer spaces, we would like to start being able to do the calculus on this manifold. And in order to do that, uh, we would like to have things like, give me 1 second. Right. I have some notes on the other screen. I'm just flipping through them. Yeah. So we would like to set up calculus on the manifold. And so before we set up the calculus, one thing I want to talk about is this idea that's going to keep coming up in this lecture and going forward. And something that we do a lot in math is we're going to use the properties that we have in Rn, where in the space that we've already have very well defined um, uh, properties, objects, and operations on, and we're going to lift them into the manifold. We're going to keep doing this over and over again. We're going to say, okay, well, we want to define this. Well, it's defined in Rn. How can we take it from Rn to our manifold? So that's kind of how we're going to do. We're going to define the calculus on the manifold as well. So to set up calculus, we need functions on the manifold. And we need um, smoothness, or I mean, in general, you want the functions to be CR, or you can have them be C infinity. C infinity is the goal here, and ideas of like differentiability. So I don't know if this is the only way you could do this, but a very convenient way to do this is to define coordinates on your manifold. Okay, so um, right. So far, what we have as a structure, so we have Hausdorffness, we have second countability. We're just using those for discluding spaces that we don't want to look at, and so the main thing that we're going to leverage is the third property, which is that if we take an open set from the space, then we can map it to Rn. So I'm going to illustrate the concept that we're going to do using an example. Again, our favorite, a sphere. So let's say that we wanted to put coordinates on this sphere. And the only thing that we had to go off of to make those coordinates is that we know that the open sets on this sphere are uh, are mappable to well, in this case it would be R2 because the sphere is two-dimensional. So let me fix that up a little bit. Right. I don't know, that might have made it worse. Right. So uh, we could think of taking this like bowl-shaped area at the bottom and think about this 3D section of the sphere. We could map that to R2, and as we grew this space, um, we could map it all the way up to, but not including this point at the top. We'll call it N for North Pole. But once we get too close to the North Pole, well, once we include the North Pole, we can know, like, we can't any without. I'm not going to get into the math of this, but we can no longer create a homeomorphism between that open set and R2. So we have to exclude this point N. So um, so that forces us to take a second open set, or maybe center it around N, where you have a second open set that goes to a second copy of R2. We can do this because we know that each open set is going to have a mapping to R2, but now we have this second copy of R2, and basically what we call these, what we call this thing, the map, is these are called charts, and they work exactly like charts. The reason I picked a sphere is that the analogy with the surface of the earth is very apt here. We just like how we can't chart the surface of the earth completely with one map, we can't chart the manifold with one map. So what we do is we take as many charts as is required, or you can have more than is required, but there's a minimum number of charts that you need to cover the entire manifold. So once we cover the entire manifold, there might be parts where, well, we've grown this blue region. So let's say it's now this big. It's not like they could be equal size, but it doesn't really matter. But notice that there's this overlapping region, which I'll highlight in yellow. So what we will want to do is to have there will be coordinates that we can define using like the coordinates on R2. We're going to lift the coordinates on R2 onto the chart, and then when we move from on the manifold from a place where we're on the first chart to a place where we're on the second chart, when they overlap, we're going to switch seamlessly from one coordinate to another coordinate. And seamlessly requires some aspect of compatibility. And so that compatibility is what is something that we're going to need to. I didn't write that correctly. Yes, compatibility. And we're going to have to worry about the compatibility of these charts. So the function there's going to be a function that takes us from one chart to the other, and we're going to call that a chart transition map. Yeah, and those chart transition maps have to satisfy some suitable definition of compatibility. And so, yeah, so let's get onto it. So what is a chart or a coordinate chart? So let's take an open set U subset of M, and so I'll just write open here just as a mnemonic. And we take this pair U phi U, where U is that, sorry, this should be UP. In fact, it doesn't need to be. Let's take that off. Where phi U is a map, phi U goes from U, which is a subset of M, to Rn, where n is the dimension of the manifold. It's a n-dimensional manifold. So I feel like I forgot to talk about what the dimension of the manifold means. Well, if subsets of M are homeomorphic to Rn, then we call the M an n-dimensional manifold. That's so M is an n-dimensional manifold in this case. Okay, so this is the homeomorphism associated with that local neighborhood. So that's a coordinate chart. That takes us to a copy of Rn. Now, from there, we can define something called local coordinates, which is a map that looks like this. I'm going to explain what this means in a little bit. Right. So P is an element of M, and we're taking phi u, which takes us from the manifold into the chart, and then we're composing that with this thing, which I haven't defined yet. This is called the coordinate function. The coordinate function is simply a function that uh, goes from Rn down to R, and it stands for, well, yeah, sure, R1. It stands for a function that will return you the ith coordinate uh, of the point on Rn. If you think of Rn as a ordered n tuple, it will give you the ith entry in that n tuple, and that gives us this thing which is called the local coordinates on uh, on U. Okay, so roughly what this looks like, because we've gotten pretty abstract here, we have this manifold, and we have this point on the manifold around which we have an open set. We're taking that down to, I kind of pictured the manifold as being above and the coordinate axes as being below. So I'm going to say that a lot. So we're going to go down to the coordinate axes and on R2, and let's say the point P is right kind of like over there. And so what this tells us, okay, so we don't know anything about what this strange space called M is yet. But we do know what R2 looks like, or this is a stand-in for Rn in this situation. We do know what Rn looks like, and we do know how to do calculus on Rn. So now that we have an open set on Rn and we have a point in Rn, now, well, in fact, this is slightly wrong. This should be this would be called phi u of P. Yeah. So now we can leverage that to do a lot of interesting things. But let's define the next thing, which is the chart coordinate, the chart transition map. Chart transition map. So very simply, you have two coordinate or two charts, coordinate charts, yes, and we then define a map, phi uv, we'll call it, and this goes from Rn to Rn, and the way that it goes through these, well, I don't really want to draw this a second time, so I'm going to cheat, and I'm just going to copy it from the time I drew it last. Yes, I want it as on my monitor. This is not going to be very pretty. I'll zoom in. So basically what we have here is you have the manifold you have the manifold M up here, and you have two different charts. You have the one for the blue set U here, and you have one for the pink set V. And there's an intersection between U and V, and in the intersection we have a point P right there. And in this chart, that section kind of looks like this. And in this chart, it kind of looks like that. So what the chart transition map does is that it allows us to short circuit going through the manifold by going from going from one copy of Rn to the other copy of Rn in one go. So these, if you didn't know anything about the manifold, if you were just looking at these two copies of Rn, this would just be the coordinate transformation from one of the copies of Rn to the other. And but in order to define it via the manifold, um, we have to say, well, okay, if I want to go from this coordinate chart to this coordinate chart, then I have to first go this way and then go that way, because I don't actually know how to go this way um, off the bat. That's what we're trying to define. So we take the indirect route and we say that the indirect route has to, like, the composition of these functions should be the same thing as this function. So we have to go backwards from phi u, so we have phi u inverse, and then we have to go forwards through phi v. So we get after phi u inverse, we take phi v. So we have these two uh, coordinate. So on the overlap between u and v, we can go from the coordinates x1, x2 to the coordinates y1, y2, and we also have the backwards, because this is a homeomorphism. The inverse map also exists, so we can always go backwards, which we expect to do because we have the forward transform, backward transform, right? So all right. So that is a chart transition map. The last thing that we need to do before we can define the structure to make something a differentiable manifold is CR compatibility. So this is the specific kind of compatibility that we want for a manifold to uh, so we want to do calculus on this manifold. So when we're moving from one side of the sphere to the other side of the sphere, we don't want the differentiability properties of the function on the manifold to suddenly change while we're moving. So we say we want to formalize some way in which uh, some way in which if we move from one coordinate chart to another coordinate chart, we don't lose any of those properties. So uh, right. So that's what's called CR compatibility. We take two. So we're still working with that previous picture. So we have phi u of u intersection v, and we have phi v of u intersection v. And what you can think of this as is that we had those two sets, or two open sets, and we have their intersection, and the point P is maybe at the middle of that. And there's this overlapping region, and we want to make sure that when we're moving from one to the other, that the functions are defined in a compatible way. So this would be the yellow region described in terms of the coordinates on u. U is this blue set, and this one would be the the same region but described in terms of the coordinates on v. So I'm just going to underline those for color coding. And we're going to call these xi, these local coordinates, and we're going to call these local coordinates yi. And so I'm going to use a little bit of shorthand here to make it faster to write, but we define this to be some function of the other coordinate. So this is the transformation. Oh, so this should be j. So when I do this, I'm actually just meaning x1, x2, dot, 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 xn. I'm not going to write that over and over again. And kind of definitionally, this has to be phi uv of xj. And then we take Yeah, so we take the coordinate function of it. These two things look the same, but they're not the same thing. Um, or I guess we could say it like take the ith entry of this. Okay, and we have to do a similar thing for uh, xi. It'll be in terms of yj, and this will be the opposite. Or you can think of this as phi uv inverse. It's the same thing. And so, what does it mean for two charts to be CR compatible? It means that either one. So we're thinking about two charts uh, on subsets U and V. So either U intersection V is equal to the empty set, meaning if U and V don't overlap at all, then they're always CR compatible. We can always put them in the same, well, in the same atlas that's we're going to build up to. Um, or if U intersection V isn't empty, if there's some overlap, then we need, again, here we're using this idea of lifting concepts from Rn. So now we're going to say that, well, Fi of xj and gi of yj must both be CR uh, on Rn. Did I get that right? Yeah, they must be both be CR on Rn. And being CR on Rn is something that we already know what it means. So it means that in the the regular derivatives or the regular partial derivatives on Rn have to be R of them have to exist. Um, so So that's what we mean when we want to say that they must all be CR compatible. So now we have the trifecta. We have charts, we have transition, and we have compatibility. So now we can do what we wanted to do, which is we're going to stitch together multiple charts, let's say one or more charts, um, to make something called an atlas. Okay, so what is an atlas? You take a set of coordinate charts. So u by u, and I was calling them. I'm not sure exactly if this is kosher to do, but I think it will get the point across. Um, I'm going to say that this is in an index. X is an element of an index set, which is a subset of the real numbers, which is just my way of saying that there might be an uncountable number of these. So there might be an uncountable number of these in this set, and this is what we call. I have a tough time drawing A when it's curly, but just take this as a curly A. Um, so this is an atlas if all the transition maps, if all the phi UVs are CR compatible. And then you call it a CR atlas. And there are two special kinds of atlases that we want to talk about. One of them is a C infinity atlas. A C infinity atlas is pretty simple. Instead of being CR compatible, they are C infinity compatible. So this is also called a smooth atlas. The other thing is a maximal atlas. And credit to Neon for pointing out a subtlety. Um, well, what I was going to say is a maximal atlas contains all other atlases on the manifold, um, but actually, there's a slight distinction that needs to be made here. Uh, a maximal atlas is one that contains all CR compatible atlases inside, like CR compatible to each other. So if there's any atlas, if there's any, if there's any chart, I kept saying atlases, didn't I? I'm getting tired. um, contains all CR compatible charts. Charts. So it contains all CR compatible charts, and so if there's a CR compatible chart to any chart in that atlas, so let's say U is CR compatible to V element of the atlas, then U is an element also of the atlas. That's what makes it maximal. So it contains all possible atlases that are CR compatible to any elements in any charts that exist inside. I keep calling them atlases. You're just gonna have to substitute chart when I say atlas. Um, right. Uh, we're almost there. So uh, so we're going to now define something called a CR differentiable structure, and that is simply a smooth, well, it was CR compatible, sorry, CR atlas, maximal CR atlas. And there could be more than one. There could be more than one set of charts that are all compatible with each other but not compatible with the others. So um, so the maximal CR atlas, this is called the CR differentiable structure. So if we call this, if we instead have a C infinity differentiable structure, you could also call that a smooth structure. And so if we have our original topological manifold, we say that we endow it with a smooth structure. So there's a choice here of smooth structures in general, and that gives you a differentiable, or well, in general, if we had a CR differentiable manifold, then we would get a CR differentiable right. If we had a CR differentiable structure, we'd get a CR differentiable manifold. And if we have a C infinity differentiable structure, then we get a smooth manifold. So that was a lot of detail. So let's kind of zoom out and see what we did so far. We started with a set, and then we very, very quickly transitioned to talking about a topological space. We said that topological spaces don't have rigid structure or smooth structure, so geometry or calculus. So then we set out to find out how to define something like that on there. So then we want to do calculus on this manifold. or on this topological space to turn it into a manifold. So uh, then we added uh, coordinates. We then added charts. We then added a transition maps, chart transition maps. And then we talked about CR compatibility. So coordinates plus charts plus chart transition maps plus CR compatibility gave us CR differentiable structure. And putting that on our topological manifold gave us a CR differentiable manifold. So that is the rundown. Um, we are at the 1 hour mark now. I think it's a good time to take a break at least and get some questions. And also, I want to know what people think about uh, uh, continuing. There's about a half an hour of content left. So I timed the original version of this lecture, and it turns out that it almost exactly comes to 1.5 hours. But given that I've already given a 1.5 hour lecture to myself today already, I don't know how cogent that half hour of lecture is going to be, and also I don't know if people are um, uh, tired or something like that. So yeah, you can talk in the chat or you can unmute yourself to ask questions. Right. So question from Samiha: Does the atlas need to cover the entire manifold or just compatible collection of charts? Maybe covering a part of the manifold would do. Yeah, that's something that the first time I gave the lecture I mentioned, but then I forgot to mention it this time. Yes, the atlas actually has one of the parts of the definition. So let me go back and talk about that. It has to cover the space. It has to be an open cover of the manifold. Uh, right. So let's go back. CR atlas. Yeah, I was going to draw this whole diagram and everything. So one thing that we forgot to talk about is that this has to be an open cover. An open cover is a cover of open sets and cover of uh, of M. What does that mean? So let's say I have a manifold M. To me, a manifold is really just a very weirdly shaped paint splotch on the ground. So, um, right. So let's say we think of that as uh, these open sets. I always think of open sets as being circular. They don't have to be circular, but um, yeah, they don't have to. I know that this is like kind of going outside of the space, which is not really allowed, but mm, yeah, something like that, where all the open sets together at least cover the entire manifold. We need that because we want to put coordinates on every point on the space in general. And like if you want to do a subset of the manifold, I suppose that would be a submanifold. So like you could cut off a section of it and make it a submanifold. Any other questions or comments? Things I said wildly wrong in the interest of time? It might not be a submanifold always. I see. I mean, if you were to take a bunch of uh, open sets that cover a portion of the manifold, uh, then you could get something that's not a manifold. Oh, I suppose if you took like not a contiguous uh, collection of them, maybe.
Yeah, I think what could happen is like if they're like let's say disjoint and you can't really go from one to another and uh, yeah, I think it could affect the structure a bit.
Although, I mean, open sets are or charts are compatible if they don't intersect. So I feel like
Yeah,
that. Yeah,
no, that's fine. I'm just saying that uh, like I'm not sure if that's it, if it has the structure of a submanifold.
I see. Okay,
Yeah. I
I'll have
mean,
to look into that.
like,
Yeah.
like, like like you can take charts that is like separated and you can take the intersection. I don't know if that's going to have a manifold structure itself.
Hmm.
So,
Yeah.
but it's still going to be an atlas because, like as you said, yeah.
Yeah. All right. I think I'll look into
I'm
that
not.
and I'll.
Yeah, I'm not
Yeah.
sure either. But I'm like it could be a bit sketchy in that case. Yeah. Thanks though. Your lectures were really great. So yeah, so far.
Oh,
So
thank you. Thank you. Uh, all right then. So, does anyone else have any questions? Do you have anything else to say, Arnab bhai?
no, I'm good. Yeah.
Yeah. All right.
Yeah. You can also just call me Arnob. That's great. Yeah.
Okay.
Anyway.
All right. So that's about it. So let's talk a little bit before we conclude on when we want to do the next lecture. So I was thinking at first that we did it every Sunday, but that was assuming that we were going to cover tangent spaces and cotangent spaces today as well. Um, but it seems like the first time I took the lecture, it was okay, but I think at this point it would be a little bit too much. So, but the second part is going to be a little shorter. Maybe that's fine. Maybe we can do it on a second day, and we can keep the lecture a little shorter. I think it would be pretty clean if we took it two times a week. We did the first part of the lecture on Sunday, second part of the lecture something like Wednesday. We can feel that and like figure out a good time. Maybe we could just take the second most popular day and roll with that. And have the have the second part of the lecture on that, and whatever that turns out to be, that might be less than an hour. They might not be completely balanced, but that way we keep. So lecture one will be done on week one, lecture two will be done on week two, etc., etc. um, how does that sound? I will take people's silence as affirmation. Okay then. Well then, I guess unless I change my mind or we'll discuss it on the Discord server, we'll maybe do the next class uh, on Wednesday because that was the second most popular day. Uh, but yeah, let me think about it a little bit. And I will update the lecture notes to reflect the errors. Oh, by the way, the conceptual problem that I was talking about is the distinction between uh, a topology and a geometry. The distinction is the thing that I pointed out in the lecture notes is that topologies are local, but geometries are global. Or sorry, the other way around. Topologies are global, but geometries are local. That's not true. Uh, uh, I meant to say something else and I didn't find a good word for it. Topologies are qualitative, but geometries are quantitative. That's a better way of thinking about it. Uh, Topologies only care about qualitative properties uh, of a space, like connectedness, whether it has holes and things like this. But the thing that that made me think about that is when I was doing the dry run of the lecture, I realized that, well, topologies have local neighborhoods, so it doesn't really make sense to say that they don't care about local properties. In fact, you can have local compactness and local other local properties on topological spaces, but the main thing is that the distances and such things are not well defined, and so for that you need to have that rigid structure, and that's where you become quantitative about like how far are 2 points on this manifold, what angle are these two lines on or these two curves on this manifold at, which is not a coherent thing to ask on a topology or a topological space. That's the distinction. And right now we're living in the limbo between being in a topology and being in a geometry. They're not like complements of each other. So right now we're a manifold and not a metric space. So once we introduce the metric, then we're going to become a geometric space. So then we're going to be able to do like properly like geometry. So far we've only been doing the differential part of it. Okay, so that's it. I don't want to keep you guys any longer. I'll update the notes and I'll update you guys on when the next lecture is going to happen. All right, have a nice night, and see you.